Sorry, a math symbol?
Yes. Another math something. Z-score.
Z-score, there you go.
dy over dx.
Okay.
Dx.
All right, so you have done some stuff with linear regression in the past. Very nice. Very nice. You've done stuff with linear regression in the past, right? Mostly you used a calculator and you had no idea of what exactly it was doing, but it gave you a line that was supposedly the line of best fit, and then you used it to make predictions for stuff. Yes? That sound somewhat familiar? All right. So we're gonna talk about where that comes from and how it works and when it's appropriate to use it, because some of the times you used it in the past, it probably wasn't appropriate to use it. Okay, but it made a good example. So on this scatter plot below, one of the things that's natural for us to want to do is kind of come up with a nice simple model for this, a linear model, because linear models, well, it doesn't get much easier than that, right? You've been doing linear equations of some kind or another since you were in 7th grade. Okay? So something to keep in mind that some of you lost some points for on the test is that a model is not reality.
Yes.
You have read this in the book multiple times, and I can't remember who it is that said it, but he said, all models are wrong, but some are useful. Okay, I know that's been in the text multiple times.
Some philosopher.
Actually, it was the statistician, but
Really? Oh,
yeah.
Same thing.
Same difference.
Might as well be a philosopher?
Yeah.
Okay, sure.
Yeah.
So models are just a simplification, and they're okay for some predictions, but they're not reality. Okay? So the estimate made, I should get out my notes to make sure I fill in all of the right words. I was like, where are my notes? I was like, why do yours not have any blanks on them?
Oh, well, if you have my name on there, then.
I'll treasure it forever. All right. So the estimate made from a model is called the predicted value. In this case, y hat. I know.
Why can't it be like y caret?
Why hat?
Yeah.
Why hat?
Why have a hat? Y caret.
So a lot of times we're going to do equations for stuff, and we are not going to be boring and use x and y all the time. We'll use frequently, instead of just even using a letter, we'll write out what it is and put that under the hat. Okay, and I'll show you an example of that a little bit later. So this line represents a linear model for these data points. Okay, notice that some of the data points are above the line, some of the data points are below the line. The difference between the observed value, that is the actual value, and its associated predicted value, y minus y hat, is called the residual. And tells you how far off the model's prediction is at that point and the direction. So if you're doing the actual minus the prediction, that should remind you of something.
Oh, standard.
Yeah, when you do standard deviation, it's the observed minus the mean, right?
Or percentage.
This kind of thing comes up all the time. And you're going to see that in a lot of statistical formulas, you're like, oh, that's just like this one. You just have packaged it differently. Okay? So, residual, same root word as residue, right? What is residue?
Like
Leftover.
It's the leftover. That's exactly right. It's how much is left over. Okay?
Or right over.
Actually, it's more like under over
Yeah.
or over under.
Over.
I'm trying to think of the quote. There's a famous quote that says, education is the residue left once much of the knowledge has disappeared, something like that. You're not going to remember all the things that you learn in high school,
Oh yeah.
right? But you have become educated, and that's what's left after a lot of that stuff goes away.
Brain works.
Okay? All right. So those are residuals. So the line of best fit is the line for which the sum of the squared residuals is the smallest, which is why this is called the least squares line. Did you ever call it least squares line in algebra? You just called it the line of best fit? Okay. So here's what we're doing. We're taking all these residuals and squaring them. Now, why do you think they decided to square the residuals? Why not just say the sum of the residuals was as small as possible?
Square it, then it takes away the negatives.
Yeah, it gets rid of the negatives for us. That's exactly right.
Why can't you take the absolute value?
That's a really good question. And I had the same question on this, and it gives you a different kind of thing. I don't remember what it was. I asked that this summer when I took my AP Summer Institute. It's like, well, why not do the absolute value? Wouldn't that get rid of the signs for you as well? And it turns out that it gives you something slightly different. But it's an excellent question. So we want to adjust this line until the sum of these squares is as little as possible. And being a visual guy, I have let's see, what do I have to do to make it go to this?
Mine doesn't work either.
I thought that if you made this live in Word and then copied it over that it would do it, but apparently not. All right, well, we'll do it this way. I know where it is. Okay, if I adjust on this, the y-intercept,
That's cool.
I can try and make this as small as possible. This, by the way, is the sum of the squares. And I can, pull it down. Oh, went too far. Somewhere in there is as small as possible. I can also adjust the slope. Maybe a slightly bigger slope would be better. Or maybe I should have a smaller slope. You can do all kinds of things to try and get the line of best fit. Notice here that I've got some residuals that are quite small now, and I've got a couple that are a little bigger. And there is a best line. In this case, well, let's see. Let's start up here and let's mess with it. So what do you think I ought to do at this point? Think I should move it up, move it down, or adjust the slope?
Slope.
Okay. So, ooh, that made it smaller. That's still smaller. That's about as good as I can get with that particular y-intercept. So there will be a slope and a y-intercept that minimizes this value. That's not too bad. Let's see, what is it actually? Oh, there's what it should actually be. Not too far off. So we would have had to have gone this way, which seems counterintuitive at first, but then done like this.
You're pretty close.
And see how that knocked this one's size down quite a bit, but kept these pretty small? Okay. That's why this is called the least squares regression, or just a linear regression. I always liked this because I remember trying to understand why it worked. And then once I saw that, I was like, oh, you're just trying to make all those squares as small as possible. Got it. And there's two things that you can adjust. So when you're doing a line of best fit, this is something you may want to highlight or something because it comes up now and then. The line of best fit must go through the point. What is that? X bar, Y bar, what is that?
Mean of the x and mean of the y.
The mean of the X and the mean of the Y. That means that if I could figure out the slope, I already have this point, I could get the regression equation, or the line of best fit equation. So, how do they come about this? Well, I'm going to go through a lot of the background information, and then we're actually going to talk about how it is that you could get this line of best fit. So, first of all, notice on this, if we were to do the z-scores of all of these points, okay, what is it that a z-score measures? Right, the number of standard deviations the point is away from the mean. So we could do the z-scores for x and the z-scores for y, and then plot a whole bunch of points. When we do that, then the line of best fit is going to pass through the origin and have a slope of r. What the heck is r? Well, r is just going to be the slope of that line. And we'll talk more about what it is in a moment. Hang on just a second. Yeah, I'm sorry. Forgot that we'd already done that. One of the problems with working in 3 different places at once, where you are, where I am, and writing notes, and where you want to be, is I forget what we've done. Yeah, that's the correlation coefficient from chapter 6. I forgot that we've done 6 already. It turns out that the slope of the line when you do this as z-scores is the correlation coefficient, which is pretty interesting that those two would be the same. So that means that for each standard deviation away from the mean in x, we predict that the y value will move r standard deviations away from the mean in y. And since r has an absolute maximum value of 1, each predicted value of y is closer to its mean in standard deviations than its corresponding x was. That's a lot to take in. Okay, but let's think about that for just a second. So the predicted z-score for y is going to be r times the z-score for x in order to get our line. R is always between -1 and +1. So if z is 1 standard deviation away and r is 0.75, then my z-score for y would be 0.75 standard deviations away from its mean. So in other words, if x is 2 standard deviations away, we'll never predict that y is going to be 2 standard deviations away also. It's always going to be less than that. And part of that is, it's not a perfect prediction model, is it? So we want to go, okay, if we're going to guess, we're going to guess a little smaller. We're not going to guess too big. So this property is called regression to the mean. Those of you who are into sports have heard this before. They frequently use it the wrong way. And this line is called the regression line. Typically in sports, the regression to the mean is you have someone who one game goes off and hits 4 home runs or something like that. If you're trying to use that game to predict the next game, well, it's going to be less than 4 home runs, because 4 home runs is way outside of what they normally do. It's many standard deviations away from their average per game. So again, and I said this a minute ago, if a particular x value is 2 standard deviations away from the mean in x, the model has a predicted value y hat that is less than 2 standard deviations away from y bar. Okay? So, and again, the reason for that is unless we have a perfectly linear scatter plot of the data, not all the variability in y can be explained by variability in x. We're going to come back to that idea in a little bit. So, we're going to come back to that right now, sorry. The percentage of variability in y that is explained by the variability in x by the regression line is r squared. You take the correlation coefficient and square it. So, for example, in a linear model used to predict attendance at home games for American League teams in 2010, from the number of wins the team had that season, we get an r squared value of 0.284. That means that for this model, 28.4% of the variability in attendance is accounted for by variability in wins. Notice that that also means that 72% of the variability in attendance is not accounted for by the wins. Okay? Which is true, and I know not all of you are sports fans, but even if you're not, you'll know that, for example, at pro football games, even if the team sucks, there's a lot of people there. Okay? The variability in the fans is partly due to how well they're doing, but only partly. Partly it's because it's an event and people do business there and all kinds of other things, or the weather was nice, or someone gave us the tickets, or any number of other things. Okay, page 2. So since the percentage of the variability that is explained by variability, percentage of variability in y that's explained by variability in x is r squared, the percentage of variability left in the residuals is 1 minus r squared. Okay, this next part, I'm going to take you through all of it, and I don't think you'll ever have to do all of this for a problem, but you will have to do parts of this. Okay, so we'll go through this and then we'll leave the last page for Monday. So most of the time, and you did this in algebra, you got the regression equation by using your calculator, right? And did you look at r or r squared? Did you look at the correlation? Pardon?
Sometimes I look at it, but I wouldn't always.
But you didn't talk about it as part of the class?
And you said algebra?
Yeah, I'm guessing it was in Algebra 2. Maybe it was in pre-cal.
We mentioned it sometimes,
I don't remember.
right? I think we talked about it a lot more in physics.
I do remember in physics, like on the
Yeah,
graph,
because
the
we always
correlation.
plot some data and see how close we get to, a best fit line.
Oh, okay. So you've done line of best fit in physics?
Yes.
Yes.
Okay. So here's how it all works. It's all statistics. Okay, which is why you've just done it on the calculator before now, because you didn't know how to do it. So I'm going to take you through how you could do it for a set of data, and then I'm going to talk about how much I would want you to be able to do on a quiz or a test. Okay? A lot of this is going to be review for you, or at least should be. We shall see. So, for a set of data containing coordinates x, y, first calculate the mean and standard deviation for both x and y. I'm not going to go over how to find the mean.
Why not?
The standard deviation in x, do you remember how to find that?
The sum of all values, well, the sum of y minus y bar squared over n minus 1 and the square root of all of that.
Yes, sir. Well done. Except it was x.
Oh, yeah. Same thing.
And again, much like we did for the line of best fit, we squared it to get rid of all the negatives, so that when we added it together, we didn't get a big pile of nothing. Okay? And the corresponding equation from y. From these, we could standardize every point's coordinates. How do we find a z-score in x?
X minus x bar over standard deviation.
Right. So it's x minus x bar over the standard deviation in x, comma, y minus y bar over the standard deviation in y. Remember, we talked about how to find the correlation coefficient. Anyone remember that one?
Something times something over n minus 1.
Yeah, something times something over n minus 1.
Or the sum of all something times something.
Well, we just found the z-scores.
Z-score times z-score.
Yeah, the z-score in x times the z-score in y. That's one where I don't think I've ever calculated that by hand.
Now that seems awful.
Well, and unless your data set is pretty small, doing all of these things to a whole bunch of data is pretty ugly, right?
Too much.
So then, if we plot all the standardized points, the resulting scatter plot is centered around the origin, because remember, when you do z-scores, the mean is 0. So the mean of the x is going to be 0, and the mean of the y is going to be 0. So this is all going to be centered around 0, 0. And the line of best fit has a slope equal to the correlation coefficient, r, giving this equation of z sub y hat equals r times z sub x. Okay? Now, we need to put this back into real units for the regression equation. The slope of our line, and your book writes this differently than I do. I write it as r times the standard deviation in y over the standard deviation in x. They write it as r times the standard deviation in y over the standard deviation in x. It's the same thing, obviously. Anyone want to guess why I like this one better?
It looks better.
Yeah, because I am all about the looks. It's because slope is changing y over changing x.
Yeah.
And it reminds me of that. So I have this times the standard deviation in y over the standard deviation in x. It just makes more sense in my head. So remembering that the regression line will contain the point x bar, y bar, we can substitute those values and the slope into the general equation of a line, y equals b plus mx, and they do it b plus mx instead of mx plus b, and solve for the y-intercept. In the end, that's going to give you this equation. Y hat is equal to b sub 0 plus b sub 1 times x, where b sub 1, the slope, is r times the standard deviation in y over the standard deviation in x, and b sub 0 is equal to the mean of y minus the slope times the mean in x. So, what is it that I would expect you to be able to do? If I was to give you r, the mean in x, and the mean in y, I expect you to be able to write the equation from there. Okay? I would not make you calculate r or, and calculate the standard deviations and the z-scores and all the things you would have to do for that. So basically, from summary statistics, you should be able to write the equation. But I'm not going to ask you to take a set of data and write the equation from that. Does that make sense? Everybody with me on that? So if you have r, the standard deviation in y, the standard deviation in x, the mean of x, the mean of y, if you have all 5 of those things given to you, you should be able to write the equation for the line. And that was really bad writing the x bar and the y bar underneath those because it looks like it's fractions now. Okay, once you do that, the slopes are always going to be expressed as y units per x units because its slope is changing y over change in x. That hasn't changed. Okay? From our previous example of attendance and wins at American League baseball games, the slope would have units of people in attendance per win. Now, usually, but not always, usually the intercept of our line has very little meaning in context. Occasionally it will, but usually it doesn't, partly because that's usually outside of the expected data values. going back to the American League Baseball, I don't care how bad your team is, in baseball at least, everybody wins sometimes. So talking about what would happen when a team had 0 wins doesn't really make any sense. Okay? Or if it happens to be one where you're using the year as your input value, as your explanatory variable, well, okay, so you're doing, I don't know, the population of Glendale, Arizona by year, and you're doing a time plot for that. Substituting in 0 means, all right, well, the population at Glendale at the birth of Christ was, right? It really doesn't make any sense, does it? Okay? So a lot of times it's the intercept isn't going to mean much. The slope always tells you something, but the intercept sometimes not nearly as much. Okay? All right, so to use a regression model, there are 3 things we're going to look for. First of all, what kind of variables do we have to have?
Yeah.
Quantitative variables. The second one is the straight enough condition. Do I have something that has a strong, or at least moderately, maybe even a weak, but it's got to have a linear association. If it doesn't have a linear association, writing a line of best fit is moronic. Okay? And the last condition is the no outlier condition. If you have an outlier and you write an equation of best, a line of best fit, it's not really going to fit very well. It will, if the outlier is above the data, then your line of best fit is going to overpredict all the time. If it's under, it's going to underpredict almost all the time. And that's not good. All right, we'll pick up with that and look at residuals, more residuals on, this will not take long. We'll go ahead and do it. And then we'll spend more time on Monday talking about the test when everybody's here, when I can fuss at everyone specifically. All right, so remember that the residual is the observed value minus the predicted value, or symbolically, E equals Y minus Y hat. And you're like, why E? Well, the flip answer is, and they tell you this in the book, R was already taken, right? But the other reason is it's the error. So when you're looking at a scatter plot of residuals, the residuals should not show any pattern whatsoever. So like this one, this is a good residual plot. The residuals are kind of all over the place. This, not so much. See how tightly packed the residuals are at first? And then they kind of fan out? That's not good. That means this was a really good model at first, and then it started sucking more as it went to the right. How about this one?
There's like sections.
Kind of a
It doesn't look
parabola.
Yeah, if you kind of look at the form of this, there's a curve in it. So for this, the line, since I have negative residuals here, at first the model overpredicted, then it mostly underpredicted, and then it overpredicted again.
Oh, I'm looking.
Yeah, that's probably not good. Something that I haven't noticed in the homework needing very often is this. I get the feeling it's going to come up again sometime, but I just don't know when. That the standard deviation of the residuals, S sub E, is the square root of the sum of E squared over n minus 2. And you're like, wait a minute. Why didn't we subtract like we normally do for standard deviation? Well, it's because E bar is 0. And you're like, why is it n minus 2? Well, because we're using this to get a line that has both slope and a y-intercept. So there are two things that we're predicting out of this one idea. It turns out the more things we're predicting, the larger the number we'll subtract here. If we're predicting 3 things, we're going to subtract 3. We'll talk about that much later, like next semester when we talk about degrees of freedom. Have you done that in biology?
We did degrees of freedom. For, I don't remember what it was. Chi-squared or something like that. Maybe not that. I remember doing something.
You did chi-squared regression?
Yes.
Cool.
Chi-squared.
Yes, we will do chi-squared regression in here.
Oh, fun.
And I'll explain why it works as opposed to lots of hand waving. Which, I mean, fair enough. It's not a math class. So, one of the things you don't want to see also is your book calls it "Does the plot thicken" condition, which is really funny. But have you ever heard that phrase, the plot thickens? Okay, so what's happening is the residuals start to spread out, or they're really spread out and then they get better later. Sorry, from your perspective this way. Then that's not good either. That's not a good linear model then. So, and again, it's a lot of times you can't see it on the original, but when you graph the residuals, you can see it. Okay, and one of the things that you can do in stat plot is you can keep the residuals after doing a line of best fit. Let me see, do I have one up here? Yep. All right, so I'll show you how it works. What I can do is, let's say I want to make a scatter plot for this particular one. And actually, instead of doing a scatter plot, I'm going to go ahead and have it find the linear regression. Okay? I'm going to do a simple linear regression. My x variable is going to be the year. The y variable is going to be the percent smoking while pregnant, which fortunately has dropped to almost nothing.
They like asking smoking problems, though.
Pardon?
I see them talking about smoking a lot.
Yeah.
Hockey. That's cool. Hockey.
Yeah.
I'm going to do a fitted line, and I'm going to tell it to save the residuals.
Like the exclamation at the end.
It's
So-
happy to compute.
It will do your equation right here.
Wow.
And it'll show you
Oh.
the fitted line
Very nice line.
with your scatter plot. You can also do a graph of the residuals. So I'm going to do a scatter plot of the year versus the residuals.
I mean, that's solidly
It
just
looks like a dinosaur footprint.
Yeah, and you're like, okay, that's not bad.
Yeah.
I don't see a real super big pattern, although it kind of dips here.
And it goes up.
And it goes up.
back down.
I'm not crazy about this one. And if you go back to this, you're like, oh, look, above, all below, all above. You're like,
They could have done it if it was like this a little more.
This is the line of best fit.
Yes, it is better than
It makes me want to take the inverse sine of all of this to see if I can straighten it out.
Does it?
It does. Well, does this not kind of look like a sinusoidal kind of thing? It's a woo-woo. All right. So all cool things that you can do with StatCrunch. All right. Any questions? Okay,